Welcome to our tutorial video for Physics 135A for Tuesday, September the 21st. Today we're going to do a simple PHET exercise involving the range equation from the reading, as well as data linearization and graphical analysis. So let me direct your attention to slide 22 of the Unit 2 lecture notes. And I'll read the first part. Let's try gaining visual intuition about projectile motion through the following program. And if you click on this link, it will take you to the PHET simulator for projectile motion. Clicking play will load the following four tabs. There's intro, vectors, drag, and the actual lab. So intro will allow you to explore the tools. So for example, we can change the height of the origin being where the location where the projectile will begin its trajectory. So let's lower that to 0. You can control the initial angle, let's pick 45 degrees, and the initial speed, v initial. You can also change the type of projectile in the top right controls. Then we can turn on air resistance, but we'll save that for later. You can add vectors and look at acceleration, velocity, etc. So if we hit fire, then we see the parabola. We can increase the initial speed there, so I'll double that speed. And it looks like the object goes much farther. For just a factor of 2 increase in speed, it seems to go some huge factor farther. So we're going to figure out why. And in particular, if you look at the range equation, this is section 3.4 of the reading. So the range equation 3.71 says that the horizontal um, the horizontal displacement of the object goes as velocity squared times sine of 2 theta initial divided by g. So what we're going to do is put that to the test. We're actually going to figure out the angular dependence and the initial velocity dependence on the range. So if we go to the slide, this equation can be derived. That's derived for you in the book, and also we can talk about that in class. I'm going to skip that part. But instead, we'll go to step 2, where we're going to plot the range versus initial velocity. We're going to fix theta. So just control for theta and vary only the velocity, and then shoot the projectile and record the horizontal displacement where the projectile lands. So let's prepare our spreadsheet. We're going to zoom in a little bit. We'll say initial velocity for our independent variable, and then range for our dependent variable. We should always put the units, so let's add the initial velocity will be in meters per second, whereas the range will be in meters. So let's make sure that's nice and clear. And then it looks like we can vary the range from 0 to 30. Now I'm going to recommend let's erase the tracks. I'm going to recommend a larger angle here, just so that if you do a big speed, let's even go to like maybe 80 degrees. If you do a larger speed, then the ball may shoot way up in the sky, but what goes up must come down, and you actually will get the range. If I had changed the angle to something like this, the ball would land off the screen. We wouldn't actually get a measurement. So let's stick with, let's say, 75 degrees, and we'll start with maybe 5, 10, 15, 20, 25, 30. Maybe increments of 5 meters per second is a reasonable guess. So let's go with 5, 10, 15, 20, 25, 30, 35. Can we go to 35? What's the maximum? Nope, just 30. Alrighty, so let's get the range for 5 meters per second. So we'll place that at 5, hit fire, and then this tool here is convenient for, like, you could use the ruler, or you could use the landing pad, but this tool actually gives you the values of that particular point. So the range was 1.27 meters. All this program is doing is applying the force of gravity down while giving the constant velocity to the right. So if you think about the trajectory here, this initial velocity has an initial angle of 75 degrees, but the horizontal component, that is the x component to the right, is constant. It never changes, but the vertical component will change in velocity due to the acceleration of gravity. So at each time step, the simulation is just modifying the velocity and then stepping time forward. It does not know the equation of the parabola a priori or to begin with. And so where it lands should be controlled only by the initial conditions we give it, and it's not using any particular formula for the range. So we got 1.27 for 5 meters per second. Our next speed is 10. So let's fire. Range. 5.1. What's interesting is that if we double the velocity, we don't get a doubling of the range. We get something more like a factor of 4. If I take 1.27 times 4, that's very close to what we got, 5.1. So it looks like as though this is a scaling relationship where the velocity is squared. So if you double the velocity, then you get a factor of 4 increase in range. So if I were to triple the velocity, I would get a factor of 9. If I were to quadruple, I would get a factor of 16. So in other words, the velocity should be squared, and it looks like already we're on the right track. So let's go to 15 meters per second, fire. The ball spins a lot longer in the air now. So the range was 11.47 meters. We'll go to Excel, 11.47. And then erase, 1, 2, 3, 4, 5, fire. So the ball is going to spend some time above the screen now. Range, 20.4, 20.39 meters, and then 1, 2, 3, 4, 5, fire. Oh no. So so it's not quite visible 31 meters, but it's a little bit more than 31 meters. How about we break out the ruler? Just to be certain, so we'll place the ruler's origin right there, and then we'll stretch the ruler all the way over here, and we get something like 31.82 meters. That seems consistent with our first measurement, 31.8. 31.8. Looks like we won't be able to do 30 for the initial angle, so let's stop and reset. Now we have some pieces of data here. We can plot these. Let's highlight the data, and I'll insert a chart, and it might look a little different on your copy of Excel. I'm actually using the free version of Excel called LibreOffice Calculator, Calc. And so I want the scatter plot. That's the correct amount of data. I don't want a legend. For the title, we'll do range in meters per second versus velocity. Oh, sorry, meters per second, and range is meters. And then for the x-axis, we have a chance to label that, so we'll say velocity in meters per second versus, and then on the y-axis, we'll say range meters. Finish. Now that's clearly not a linear trend. Let's see if we can change the shape of the graph here to make that more evident. Can we just go like this? Yeah. So that's clearly not linear. So we're going to have to try a different, go into the graph here. let's try to insert a trend line, but we'll do a polynomial of degree 2, and we'll want to show the equation. Okay, go. So that looks like a very good fit. I think maybe we won't learn a whole lot from the equation, but just to see that it's there's some relationship between f of x, the range, and the velocity x, and that goes as x squared. The fact that we're not starting from 0 introduces this other term, but it's really tiny, and then there's almost no y offset. So um, in any case, the idea here is to show that it is a quadratic relationship. And and that is what we expect from the formula for the range, that range goes as v squared. Now, one thing that we can do, though, is we can linearize the data. So let's make a column that says v squared, and then we'll just copy the range over here. So the range will just be equal to whatever's in that column, and we're going to copy the data over. This, however, let's do v that times that, so v squared. So 5 times 5 is 25, and we're going to look at um, the graph of v squared on the x-axis and range on the y-axis. So we'll highlight this data, and then we'll insert a chart. Next. I'll skip the title, but what we want the XY scatter version. Take away the legend, finish. Now notice that this is a linear trend. So if we insert a trend line, we'll go with linear. That's fine. Now it's very linear, right? So before it clearly wasn't linear, but now we've somehow linearized the data. Well, if you look at the formula, r is directly proportional to v squared. So if you plot r versus v squared, then the slope will be whatever it remains, but it should be a linear relationship. So hopefully that makes sense. If let me type it in words, if r is equal to y and v squared is equal to x, and then let's say the slope is equal to sine 2 theta over g, then this graph at right is essentially y is equal to mx. And so if you just make the thing on the x-axis be whatever is directly proportional to y, then you should get a linear relationship. Now that's going to become useful here in a moment when we test our theta relationship. So let's fix our initial velocity. Again, we'll take the origin all the way down to 0. We're going to vary theta now. I think we're going to want to choose a relatively low velocity, maybe 10 meters per second on the low end. And we'll start with, we can go from 25 degrees all the way to 90. Let's start with 25. We'll call this column angle in degrees, and then we'll say range in meters. And I think we'll go 25, 30, 35, 40, something like that. So for 25, we fire. We'll use our range tool to find the last point there. Range is 7.81. And then if we go to 30 degrees fire, then we're going to get a slightly higher range, 8.83. Need to make a period 8.83. And then 35 fire, get a slightly higher range there, 9.58. 40 fire, 10.04, 45. Intuitively, we expect this to be our highest range. 10.19. And I think from now on we should erase, and then 50 degrees fire, 10.04. That number looks familiar. And then 55, 9.58. 60 fire, getting smaller ranges now, 8.83. 65 degrees fire, 7.81. So it's now time to graph this. Let's insert a chart of the scatter plot variety. Next. Don't want the legend. Let's skip the titling for now. Oops. So that is interesting. We might think of that as a quadratic. It's actually not what's predicted by the formula. The formula says in particular that it should be, if you hold v squared constant and g is always constant, then sine 2 theta would be the way to go here. It's a sine function. The sine 2 theta function will peak at 45 degrees. If you just graph sine 2x versus x, then the peak is at 45, not 90. But if we try to show that or prove that by fitting a trend line, insert trend line, linear log exponential power polynomial moving average. We don't really have a sign. We can't choose sign of anything here. Our choices are kind of limited when it comes to the fitting functions. So what if instead of plotting that, what if we linearize the data? After all, the expectation is that r is directly proportional to sine 2 theta. So once again, we'll copy the range over a column here, and that's going to be equal to that, and then we'll just expand that data like this. Now here, we're going to say sine 2 theta like that. Let's say sine of 2 times, and we'll take this angle. Now let's convert to radians. So we'll say times 3.14, that's pi, divided by 180. That's how you convert from degrees to radians. You multiply by pi and then divide by 180 degrees. And so we've got our sine 2 theta there. And now we should plot this versus this. We'll go to insert chart like that. XY scatter, next. Don't want to display the legend, finish. Notice that that is a linear relationship now. Oh, I see. Many of the data points are very close to 1, and so they're stacked on top of each other over here. But if we insert a trend line, now we can choose linear, okay, and that is a good looking fit, right? So in other words, range is on the y-axis. What's on the x-axis? Sine of 2 theta. And so by linearizing the data, we've actually shown that the range is proportional to the sine of twice the initial angle. So your goal for this assignment is to recreate the plots for the v squared dependence and the angular dependence separately. So I want you to produce these two graphs and bring them with you to class. So this has been the tutorial video for the latest PHET activity in Physics 135A. If you have any questions, don't hesitate to email me at jhansen2@whittier.edu. Thank you for your attention.